Welcome everyone to OCT and Ophthalmology in the Age of Artificial Intelligence, a webinar hosted by Photonics Media. My name is Robin Riley and I'm the Photonics Media web editor. I would like to introduce Dr. Nishant Mahan, Vice President of the OCT division at Wasatch Photonics. Nishant will be speaking today on artificial intelligence and how it is changing the medical imaging field. If you have any technical issues during the webinar, please log out and log back in to rejoin. We encourage you to ask questions throughout this presentation. Just type your question in the question box to the right of your screen, and we will answer as many as possible at the close of the webinar. Most of you received instructions yesterday on how to access a zip file that Nishant will share with you during his presentation. I will make these instructions available in the chat box shortly after we begin. And now I would like to introduce our speaker, Dr. Nishant Mahan.
Thank you, Robin.
Welcome, Nishant.
Thank you, Robin. Thank you, and thanks everyone for listening in from around the world and joining this webinar. I'm really excited to be presenting on the topic of artificial intelligence and its role in ophthalmology and imaging techniques like OCT. I'm sure most of you have heard about recent advances in the field of AI. The AI community itself has very collaborative and academic foundations, and there's a strong sense in regards to taking the developments and sharing with our own application domains. And I hope we are doing a small part of it today in this presentation. I will start the presentation with a video about a seminal moment marked by a very recent event that went unnoticed for most of us, but has strong repercussions across many different fields. It doesn't relate to medical imaging at all, but to the game of Go, an ancient Chinese board game that is long considered to be an ultimate representation of human intuition and thinking. I will request you to watch this video carefully as we get started, and we will take on from there.
Go is the most complex game pretty much ever devised by man. Beating a professional player at Go is a long-standing grand challenge of AI research.
All is a 9-dan professional. 9-dan professional is the highest rank that you can achieve in Go. The ranking system. Fan Hui, who is the European champion, is just a 2-dan professional. On the other hand, at the very top, Lee Sedol is 9-dan professional. Lee Sedol is to Go what Roger Federer is to tennis.
Lee Sedol go to smoke, and AlphaGo just play. It don't think about the opening will be there or not. So Ajab sees AlphaGo plays the move 37, and Ajab puts the stone in the board.
와, 정말 생각지도 못한.
Value.
That's a very surprising move.
I thought it was a mistake.
AlphaGo said there was a 1 in 10,000 probability that move 37 would have been played by a human player. So it knew that this was an extremely unlikely move. It went beyond its human guide, and it came up with something new and creative and different.
알파고는 사실은 확률적 계산을 하고 그냥 이기기 위한 그런 머신에 불과하다고 생각을 했었는데 그 수를 보는 순간 아니구나. 충분히 알파고도 창의적이다. 정말 아름답고 바둑의 그런 아름다움 잘 표현한 수고 굉장히 창의적인 수입니다.
So thanks so much for watching the video. As you can see, the impact of this has been observed by the governments and big corporations around the world. And this was indeed a flagship event in regards to capability of machines to act like humans. This step change is having influence across many different fields on many applications. And one field where acting like human or human intuition is really important is that of healthcare. Amongst them, artificial intelligence has really led the way in ophthalmology. One of the key reasons is that in ophthalmology, we have lots of data and lots of diseases. Almost every individual alive suffers from some kind of ophthalmic disorder in their lifetimes. In this presentation, we will see various type of ophthalmic conditions which have been influenced by AI research. So let's start first by a question which was asked in an important study a couple of years ago with the same group who actually developed the Go machine about can a machine make clinically relevant diagnosis and referrals like a expert human practitioner? And this machine used the OCT imaging technique. So the only piece of information available to machine was the OCT images of the retina, and they had to make human-like diagnosis and referrals. So the exact goal for them was to make an expert-level automatic diagnosis where they would try to predict 10 different retinal disorders and try to make a reference based on whether the conditions of the patient are urgent, semi-urgent, routine, or observational. So how do we define the metrics for it? We first want to define a gold standard, and that is given by looking at the patient's initial images and their final diagnosis retrospectively. Once you are sure what the final diagnosis was, then you can say that based on the images, what kind of reference decision should have been made, whether it's urgent, semi-urgent, and what should have been the original diagnosis. So we will see if machine can make a similar kind of diagnosis. So let's look at the results from this study on human experts versus the machine. So the test set was of 1,000 patient images, and the criterion was diagnostic accuracy. So we will look at the error rates, how many times a particular practitioner or a machine learning algorithm got the results wrong. So that means the lower number here is a better result. So first, let's see if the practitioners have only OCT information, and then they try to make a reference, and that is compared with the final diagnosis. And we can see that we have 4 optometrists and 4 retina specialists here, and they all have certain degree of error. Obviously, retina specialists with more experience with retinal diseases perform slightly better. Then the practitioners were given OCT plus fundus images and the patient notes, and the similar test was performed, and naturally the performance improved across the board. Now, the next question is, how did a machine which was trained to do these things using artificial intelligence perform, and that only had OCT data available to it? In this study, the machine performed at the level of the best retina specialists out there with only 5.5% error rate in making the references. So a quick description of what this study did. They took OCT images and segmented it into different portions by using around 800 training data sets, and those segmented portions were then used to train onto different referral suggestions as well as different disease conditions. This training was done using about 15,000 data sets. The details of this and similar kind of techniques will be discussed later in the presentation. So that was just an example of how machine learning is influencing so many different fields, and we can clearly say that we are living at boom time for artificial intelligence. We can look at any metric we want. The number of AI startups have grown exponentially, increasing by about 5 times over the last 5 years. The VC funding has grown exponentially, going about 4 times from last 5 years. The number of job openings as a percentage of total job market have increased exponentially. So has the number of patents being filed and the number of papers being published in AI research. And the goal of this presentation is for us to be able to understand the growth of AI, what is driving in, and how it's influencing different applications. So we will look at the fundamental problem of interest, that is image classification. When something is present in the image, how good is a machine at predicting what it is? Then we will look at the key driver of these things, which are deep neural networks. We will see research works and some commercial instruments related to ophthalmology, which are powered by artificial intelligence. We will talk about some practical considerations in developing a deep neural network-based AI system, as well as we will see an example of how a deep neural network can be developed from scratch. And we will, the last portion will be a small video, and we will have separate notes for people who are not into programming to be able to understand at a top level what goes behind developing a deep neural network. So let's start with the fundamental problem of the image classification. Image classification is nothing but trying to identify what is contained in an image. So can we say if a retinal fundus image contains signs of diabetic retinopathy, or if it contains a certain object which we are well known for machine, it makes no difference. A classical test of this is done using something called ImageNet, a database of over 14 million labeled images of 20,000 different categories. These are the images which are found in real world and have categories also which are very real world, like animals, trees, flowers, people. An annual contest is held and different algorithms are entered to test the performance of algorithms in their capability of recognizing content of an image. So here are some examples from ImageNet. You have an image which can have a bird, a frog, a person, a dog, a chair, and so on. So let's see how machines have done over the years in the ImageNet contest. So here is result from 2010, where in red we are showing the human performance, and in green we are showing the machine performance. And this is again an error rate, so lower the better. So humans make only 5% error when it comes to classifying the content of an image, whereas machines had a chance of about 25%, being 25% wrong, so 1 in 4. The results were similar in 2011. However, in 2012, a step change occurred, and the performance of the computers increased by about 10%. And not only this, the winning entry was about 10% better than all others. So all others were doing same as what we have seen in previous years. But this entry from University of Toronto using a neural network called AlexNet performed 10% better than every other. And this was a very important moment in machine learning, and especially for computer vision applications like image classification. In 2013, another entry which was based on neural networks won. In 2014, Google's GoogleNet won with a 7% accuracy, and we can see that the accuracy of the systems were increasing exponentially, as well as neural networks were getting deeper with 32-layer neural network. But these were still performing worse than human performance in image classification. The 2015 was a step change when Microsoft Research Asia's ResNet performed better than human level accuracy. And this continues on for 2016 and 17 when the performance of the computers at image classification keeps getting better, and they're all driven by this moment in 2012 with the introduction of neural networks for this. So let's see what are the technical drivers which has created these step changes. What I like to call is this the triangle of AI, which corresponds to 3 key factors which have driven the growth in AI applications. The first one is the algorithms, particularly the neural networks. Especially what has changed is instead of using shallow networks, people have started using deep networks, which are the neural networks having several different layers in them. And we will definitely talk in a lot more detail about this. The second is the data, the amount of data available. As we know, with digitization and internet, the amount of data available in several different fields have increased exponentially. And this plays a critical role in performance of AI systems, particularly based on neural networks. A shallow neural network saturates in its performance after a certain amount of data is given to it. But a deep neural network tends to continue to improve its performance as the amount of data is increased, and that has been a great synergy between the big data available in recent years as well as the neural network development. The third is the hardware. The hardware required to train these deep neural networks was not readily available before, but with advent of GPUs, which became extremely popular because of the gaming and display industry, they were used for development of neural networks and in particularly for their training. It just happens that these neural networks tend to be extremely parallel, and GPUs are very good at performing parallel tasks. In fact, neural networks are called embarrassingly parallel, which means they're very easy to parallelize and perform fast computations. Okay, so we discussed the fundamental problem in image classifications. Now let's move on to looking closer at these deep neural networks. So we will discuss briefly about what a neural network is. It's nothing but a series of nodes where each node performs a simple operation and passes on to the next node. The next node takes it as an input and passed on to the next one after a simple operation. So what does one single node do? You give it an input and it gives out the output. The input is multiplied by a number called a weight, and another number is added to it called a bias. So this is a linear transformation. After that, this linear transformation is passed through what is called an activation function, and that maps it into a nonlinear through a nonlinear function. So again, we can see this one node is doing very simple operations using the weights and biases and activation functions. The important thing to note is that the weight and biases can change for each particular node, but the activation function always remains same. And it is this change in the connection between two nodes of weight and biases what defines a neural network. And the whole goal of neural networks is to find the optimal weights and biases for a particular problem. So let's take this node and combine it with all other nodes. And you can see each connection has a weight assigned to it. We will not discuss about biases. In most discussions, we only focus on the weight. So each node has a weight, each connection has a weight assigned to it. Now let's say we have some input and we know the answer which we want. We know the corresponding right answer is this one. If we enter this input to the neural network and we have these random weights, we will get some random answer, which will not be the correct answer. And what we will want is the difference between the obtained answer and the right answer which we have. Of course, we can take a simple mathematical difference, but slightly more complex functions are used. These functions are called loss functions in neural networks. And our goal is to reduce the loss function as much as possible by optimization of the weight. So we want to pick the right weight such that the difference between the obtained answer and the right answer goes down, and we obtain correct answers when we put the input. Okay, so let's say for the given these weights, we have some loss function. Then through the optimization process, we will update the weights so they all become from 0 to 1. And in the step 1, now we have a new loss function, which hopefully is less than the earlier one because we did some optimization. Then we do the next step again, the loss function goes down and the weights get updated, and the same thing again. And now we can say the loss function is really small, so that means the difference between obtained and right answers is not too much. That means we are almost getting the right answer giving this input. Now if we take this neural network and give it a new input which it hadn't seen before, the expectation is that it will give us the correct answer. So it's a very simple process, but the key point is that we can have lots and lots of nodes and lots of weights, and they all can be optimized to learn very complex tasks. So just a quick review of this. So neural networks, in neural networks, the complexity is scalable, and that allows them to run very complex tasks. The large networks require a lot of data and are good at learning extremely complex tasks with help of this data. Our goal is always to minimize the error with respect to the correct answers which are known during the training process. All neural network design is focused on how do we minimize this error with the amount of data which is available for us. During the presentation, I will also put some terms to take away so we can kind of focus on the key concepts. And then so far we have learned about deep neural networks, loss functions, and optimizer. And we will see these towards the end when we do an example. Okay, so those were simple data forms. What if we are working with images? Images in computers are represented by numbers, And you can see I just take an image, put it in Excel, and the smaller numbers are darker colors and the higher numbers are brighter colors. Now, if I have to deal with these through a neural network, one option I have is to linearize the image and put it through a neural network and get my result which I want. That is possible, but given the size of the images, this can often become very difficult. So the second idea is to use what are called convolutional neural network, where the weights are put into this kind of a matrix, where each element of the matrix can be considered to be a different weight, and then this is multiplied with the part of the image, and the result of each individual multiplication is added together to get one number. This process is convolution, and hence the name convolution neural network. Now I can move this rectangle matrix as I want and have numbers corresponding to each different position. This can be applied to a whole image to transform the image from one to another. So again, I'm taking an image, transforming it during this convolution, and the weights of the convolution matrix I'm using are what's going to define the properties of the neural network. So in a convolutional neural network, you take an input and you take them through a bunch of different convolutional filters, and we can have multiple layers of such convolutional filters called convolutional layers. In the end, let's say this was a problem where I wanted to recognize the digit present in the image. So I do want one output, even though if I put an input to a convolutional layer, the output will always be another image coming out of it. So to do this, usually towards the end, we have a standard type of neural network, which is called a fully connected layer or fully connected layers, to give a discrete output as we may require in some cases. And the whole goal of training of convolutional neural networks is to train the weights like we were doing before for standard neural networks. Another important concept to remember is concept of pooling. This is a very simple concept. All it does, it takes a section of the image, it takes the maximum value of it and passes on to the next step. So this is often used to reduce the size of outputs as we go down a convolutional neural network, which can be very important given as we go down the complexity of the network increases. Okay, so let's look at some of the famous convolutional networks in last few years which have had major impact. The one which we had talked about is AlexNet, and I kind of want to discuss some of its properties to give an idea of how does a convolutional neural network look like. So this neural network had 5 convolutional layers. You start with a convolutional layer, then you have a pooling layer we talked about, then another convolutional followed by a pooling layer. Then a series of 3 convolutional layers, a pooling layer, and 3 fully connected layers. At the time in 2012, when this came out, this was considered to be a deep network with about 8 layers, 5 of them being convolutional, and total 62 million parameters or weights to be optimized. That's a huge number and does require a GPU to be able to do it. Another important part of this publication was use of activation function, which was, it is called a ReLU, and it definitely demonstrated improved results using this activation function. Here are some other examples of important networks. In 2014, a network called VGGNet performed extremely well at ImageNet competition. This one had 138 million parameters, and the innovation was using a fixed size filter where all the filters were 3 by 3. Then we have InceptionNet from Google, which allowed use of different filter sizes, which the neural network chooses on its own, depending on the problem presented. And ResNet 152, which came out in 2015, introduced the concept of skip connections. It's an interesting concept which helps you to train a very deep neural network. Before this innovation, it was difficult to have neural networks which were very deep and train them properly. And this was, of course, the network which resulted in an image classification performance better than a human, and this was a over 95% ImageNet performance. On the right, we have the FLOP stands from floating point operations needed for these networks, and we can see that these are extremely high, requiring very computationally very heavy requirements on these networks. Okay, so some quick takeaways from here. Convolutional networks are particularly suited for images, although given their success, they have been applied for other applications as well, where you take a linear data and convert it into sort of an image. The most of the innovation has gone into trying to create deeper and deeper networks, as we know that the performance of these increases as we go deeper. The concept of pooling and fully connected layers are introduced to provide more flexibility in type of results we can obtain. So some terms which we learned during this part were convolutional neural networks, filters, or also called kernels, max pooling, and fully connected or dense layers. Fully connected layers are also called dense, and we will see this later. Okay, so the next step. So what kind of impact have these networks had on ophthalmology so far? So firstly, ophthalmology lends itself very nicely for artificial intelligence applications. The amount of data available in ophthalmology is extremely large compared to other diseases, especially the imaging data. And this comes from the fact that the data is easy to acquire through fundus imaging and OCT. As many of you probably know, there's OCT scans are done in a very high volume now, which about almost one OCT scan taken every second according to Medicare records, which shows that the actual numbers will probably be about double of that. Ophthalmology also is a window of to many other diseases. As we know, through eyes we have access to the nervous as well as vascular system of the body, which can carry markers for other diseases related to vasculature or related to the nervous system. So some of the key diseases in ophthalmology which have been researched into using AI are diabetic retinopathy, age-related macular degeneration, glaucoma, and others like ROP, as well as looking at other things like neural conditions, cardiovascular treatment planning, as well as surgical procedures. So let's look at diabetic retinopathy first. Diabetic retinopathy affects 1 in 3 diabetic patients. It is expected that by about 2040, there will be 200 million patients suffering from diabetic retinopathy. The key treatment for this is to screen the patient and them to refer in a timely fashion for appropriate treatment, which usually involves treatment of increased vasculature. There are different signs which are considered markers for diabetic retinopathy. These include hemorrhages, microaneurysms, white exudates, etc. So here is one study which came out in 2016, which used fundus images to predict diabetic retinopathy using deep learning. They used Inception 3 network, and they trained using 120 images, and 10,000 images were used for testing. Images were graded by independent graders about 3 to 7 times. Now let's look at the results here. So first we will try to study what kind of, how do we measure the results in such a case? One thing we look for is the sensitivity. That is, we don't want to miss a diseased eye. Then we want to look at a specificity. That is, we don't want to call an healthy eye diseased. And this is also studied through plotting what is called area under the curve of area under this curve, which is often which comes from telecommunications, where this is called the receiver operator curve. And the more area under you have the curve, that means the better the performance of the detection system. So in this study, 2 points were picked, both to reduce the false negative and the false positive. And you can see that, and that can be chosen depending on a particular case where the system wants to be more specific or it wants to be more sensitive. And you can see that the performance of the system, which was completely autonomous, was almost as good as the experts who were represented, whose performance is represented by the colored dots here, and the system performance is represented by the black triangle. So several such studies have been done, and AI has definitely been seen as an indispensable tool for DR screening at the moment. This is a very important work, as well as it was the first autonomous AI system that was cleared by FDA. This comes from a company called IDEX, and the product is called IDEX DR. And the Nature paper on the top discusses a prospective study for the clinical trials for this AI system, which is used for screening for diabetic retinopathy. This one trained on 1 million image patches and uses a multi-stage clinically inspired algorithm. And it definitely is considered an important breakthrough, not in ophthalmology, but in medicine in general, becoming the first FDA-cleared algorithm which operates fully autonomously. So there are a lot of studies. This definitely is not a full literature survey, but here are some of the important works which have discussed diabetic retinopathy. I'm sure there will be a lot more coming in future. So keep an eye for these. It's almost impossible to do a full literature survey of this field. Next disease we look at is age-related macular degeneration. AMD is the leading cause of blindness in the developed world. It is a progressive disease which has a diaphragm which can evolve into what is called geographic atrophy or into a wet form. Both GA and the wet form of AMD can result in severe vision loss. Nearly 15 million patients of AMD are in the United States alone. Here is an example taken which shows how the vision is influenced by AMD. As the name says, it's a macular degeneration technique, which means that the macula or the center of the eye, which is used for sensitive vision, is the one which is affected, and that results in deterioration of the vision very quickly. Here is a chart which shows how AMD can progress, and it is really the intermediate and the advanced stage of AMDs which are considered dangerous. The advanced stage progresses into geographic atrophy GA, or wet AMD, which is seen with the CNV or choroidal neovascularization. So what role does AI have to play for AMD? There are several ways in AI has been used. One is for detection of AMD using fundus and OCT, predicting progression to wet AMD or GA, as well as trying to detect the CNV. So here are some works. Again, it's a small sample list. The full literature survey is beyond the scope of this work, but this just gives us some idea. Grassman and others in 2018 showed that using fundus images, we can classify automatically the patient's condition into 13 different classes, 9 of which were less than advanced AMD, and other 3 were having GA, CNV, or both. They use an ensemble of networks, which means they have multiple neural networks built, and the final result was an average of output of all of them. About 120,000 training samples were used, with around 5,000 used for testing. Lee and others in 2017 showed detection of AMD using OCT images with a very high accuracy, and they used the VGG deep neural network, which we had talked about before. Schmidt and others in 2018 published a very interesting study on progression of AMD, where they not only use OCT data, but also genetic information and age to predict whether a patient with dry AMD will proceed towards neovascularization or geographic atrophy. Now, this is extremely important because this is of a strong clinical significance, and they had area under curve of 0.68 and 0.8, and they found some very interesting things, that the drusen-centric parameters were more predictive of CNV, whereas neurosensory ones were more predictive of GA. I'm sure similar studies in future will be extremely helpful for understanding AMD and its progression. Then Kermani and others published a very detailed study in 2018, which showed capability of an AI system using ResNet 50 to be able to detect a lot of different kind of ocular conditions, one of them being neovascularization. Here is a product which is in works, and it is from Notal Vision, called Home OCT. It is a very unique device which is supposed to be an OCT system that can be operated by the patient themselves. And the goal of this device will be to monitor the wet version of AMD. The device is supposed to carry AI-based algorithms to detect retinal fluid and to alert the physician. And given how serious of a condition AMD is, this device was designated as an FDA breakthrough device. You can learn more about the device on the website, and here's an interesting paper from the group which showed automatic detection of lesion activity in AMD. Okay, so we see the effect of what the role AI has played in diabetic retinopathy and AMD. There is an interesting problem to deal with, which is called black box problem in artificial intelligence. That means in a neural net-based artificial intelligence system, we put an input and we get an output, but we don't know how the neural network is working. It learns all the features by itself, so we have no understanding of causation of the output which is given. Important work has been done to try to figure out what part of the image is actually influencing the result. So here are some daily images. We see an image of a dog, and the map below shows what the neural network is seeing that is helping it to predict what image it is looking at. Same, if the neural network is predicting a fluid in this image, then what is it looking at that is helping it to predict that it is looking at that particular object. And the same idea has been extended to ophthalmology and fundus images as well. When a neural network predicts that it is seeing diabetic retinopathy, what are the parts of the image it is actually looking at? And a lot of different methods have been developed. The paper below is the one where the images are taken from. And you can see that in this paper, the neural network predicts that there is a moderate chance of diabetic retinopathy, and it also points out the lesions which it is looking at and it thinks are the ones resulting in this decision. So this can be extremely helpful to combine both the efforts of human and artificial intelligence machines together. And a work which came out earlier this year shows showed a study which compared performance of humans and AI by themselves and humans and AI together. So here is a result on trying to detect refractory diabetic retinopathy where a grader is unassisted. That means they have access to no artificial intelligence and they're just using their own understanding. And the sensitivity of 75% and specificity of 96% was observed. Then they were given the grades which are obtained by the machine and the image itself. And in the third case, they were given the grades and the heat maps. And we can see that the performance improves. That is, when the grades are present versus not, the sensitivity goes up and the specificity stays pretty high. And that is true as well for when we have grades and heat map present together. So this paper had a lot of interesting conclusions. One of them is that human and AI perform better together than either by itself. There was also interesting discussions about what kind of parts of the image does the AI algorithm miss and when it makes the mistakes, as well as the speed of the human graders when they are helped with the AI algorithm present with them. Okay, so key takeaway from the impact of AI in ophthalmology. I think it would be fair to say that AI is seen as an indispensable tool for DR screening in future. It is playing an important role in AMD and is also being investigated in glaucoma, retinopathy of prematurity, and several other ocular disorders. Eye is a window to other diseases, and there have been publications where eye images have been used to predict cardiovascular risk. It will be used for developing drugs, which will be helpful in ophthalmology. There are already several commercial devices in pipeline related to applications of AI in ophthalmology. So the new terms to take away from this sections will be the black box problem and locked algorithms. Okay. So now looking at some practical considerations of developing a deep learning AI system. So deep neural networks, they work with extremely large data, and those data sets have to be trained and then brings up a lot of special problems and have different resolutions for it. One key concept to understand is called overfitting. Another word called data augmentation, and then transfer learning. We will discuss what all these three mean and how they influence development of deep neural network. They all are trying to solve one fundamental problem, which is trying to match the amount of training data available to the complexity of the relationship which can be drawn between input and output. So let's see, what does overfitting mean? Overfitting means when we try to draw a conclusion too complex for amount of data which is available to us. So let's say if I have a point and I try to represent it by drawing a line through it, I can draw infinite amount of lines, and I will always be correct if the line passes through the point. But in none of those cases, the line is an actual representation of the problem at hand, because I'm making too complex of a inference of line which requires at least 2 points to define it than the amount of data which I have with me, which is just 1 point. The image here gives a similar example. You can see that we are trying to distinguish between the red crosses and blue circles, and when we are trying to draw a boundary on the right, we are making a very complex assumption about the shape of the boundary which separates these two. Although our answer is absolutely right on the data which is given to us, it is very likely when a new data point is given, we will be predicting it incorrectly based on this kind of inference. So overfitting refers to having a too complex of a rule compared to amount of data available. You can always see that you are overfitting when you have very good results on the training data which is with you, but whenever you show a new validation data, the results suddenly fall. There are a lot of techniques which are used in neural networks to reduce the impact of overfitting. These are called dropouts, early stopping regularization. Others, we will not discuss them in detail here. The next important concept is data augmentation. So, you know, it's lunchtime in some parts of the world right now, and the thing which neural networks are most hungry for is data. And the more data you give, the better the neural network performs. But in real life, we are limited by amount of data which is present to us. So a technique called data augmentation, that is, you take a single piece of data and you create different versions of it. You can flip and rotate, crop, and then do those operations in sequence to create more forms of data. Although we are not giving any new information, this is still better than having just one image. And this is often used a very powerful tool for training deep neural networks. The third concept is transfer learning, and an extremely important concept, I think, which has played an important role in popularization of deep neural networks. So if, let's say, we have a neural network and it was trained on images on cats and dogs, and it can predict whether a cat or a dog is present. Okay, that's fine. But now if I want to use a similar neural network for, say, OCT images, I don't have the option of using it because it gives an output I'm completely not interested in. And here the idea of transfer learning comes in. Instead of designing a completely new neural network from scratch, what we can do, we can only train parts of this network. And it is common to train the end part of the network which carries more complex information than the early part of network which carries simpler information. So we keep the early part of the network same and train the later part and get the output which we are interested in by having the later part designed to do that. This is an extremely powerful technique which is used in many applications and extended neural networks in different domains. Okay, so let's look at what are the key steps which one takes while trying to develop a deep neural network system. The first one is to collect data. It's extremely important for training. Then we have to label the data. That means we need to know what does each image contain, or whatever answer we want a particular input to give. So the data will be the input, the label data will be the output. Then we want to select a network architecture which we will train using this label data which is available to us. We will train the network, and then we will tune the network's hyperparameters. So hyperparameters are a bunch of different numbers associated with the network, which are not its weights and biases. So these are not trained during the training of the network, but have to be optimized to get the right results from it. Now, once the network training is complete, we want to finalize the weights and then validate its results. Most of the effort, at least on the intellectual side, goes on the training the network, tuning its parameter, and then getting the final network weights. There are important concepts called of batch sizes and epochs, which one needs to remember. If you have a lot of data, all of that cannot be entered into the network at once. So we picked manageable batch sizes. Epoch means the one full pass of the training data through the network, which for getting for updating its weights. In practice, the same data has to be passed to the network multiple times in different orders. Okay, so looking at how does one go about deploying these networks in real life? As far as the hardware and the cloud platforms go, almost all neural networks these days are trained using GPUs, and the powerful hardware is also found on cloud services like Google Colabs, Amazon Web Services, and Paperspace. On top of this, there are software platforms which are help to develop these deep neural networks at a much faster pace than coding them from scratch, as well as helping them train in a much more stable fashion. TensorFlow from Google, PyTorch from Facebook, and CNTK from Microsoft are one of more popular frameworks. There are several others, but TensorFlow and PyTorch definitely dominate the development of deep neural networks. And to make things even easier, they have even higher level libraries available on top of them, which makes programming much easier. And that what allows people to make simple networks very quickly for testing and getting an intuition into what the deep neural networks are all about. Most of these libraries are open source, that is, they have MIT or Apache licenses, and this is currently the norm in deep learning world, and it also gives a sense of the ecosystem in which the current artificial intelligence exists, where a lot of information is open source, and there is a tendency towards being able to access as much data as possible. So the key takeaway from this section is that the deep neural networks employ a lot of techniques to manage complex, large complex networks, and these include transfer learning, data augmentation, and as well as careful attention to whether our systems are overfitting or not. There are several open source platforms which are available from big companies that can be used for fast development of such deep networks. So few terms to remember from this segment are overfitting, data augmentation, transfer learning, batch sizes, epochs, and hyperparameters. Okay, so now we have gotten a basic overview of what deep neural networks are, their impact on ophthalmology, and some practical considerations. The next step would be about an 8 to 10 minute video where we will show how one can try to build a simple network from scratch using free online tools available. Many of you who are not into computer programming may not find it that interesting, but I will still recommend looking at the key steps which I put as in plain English, and try to understand what are those key steps which goes into building these networks. I think it is important to be able to see what goes behind the development of these AI systems to be able to get a better intuition as more of us continue to use them in our daily life. So here is an example of using Google Colab. You can go into Google and search for Google Colab and create a new, oops. Where's the video? Okay, starting from here. You can create a new notebook. This will automatically have an option to run a GPU in the runtime, and you can start programming from there. So you go into the Google Colab system, select your runtime to be GPU, and then you can start programming here. Here are the key steps, and we can look at this. So if you're not interested in the programming, these are the 8 key steps which we go through and to train and execute a full neural network. And you can see that the first 5 are all related to getting the data and setting it up in a right format, and the last, 6 and 7 relate to creating your model, and the last one relates to the testing. So first thing which we want to do is to install our programming framework, which will be TensorFlow in this case. And the TensorFlow 2.0, which was just launched last week, will be installed through the pip command, which we send here. And the next step would be to get the data, which should be available in your Google Drive. So many of you were sent a dataset.zip file, and if you copy into your Google Drive, you can access it from there. So the steps to mount the Google Drive are done through these commands, and after that, once you execute it, Google will give you an authorization code, which you enter here, and you can access the contents of your drive from that point onwards. Okay, sorry. Okay, so we can jump to the step of once your drive is mounted, then the next step would be to copy the data from the drive to your current workspace, where you can see on the left here. So you can see you can access the drive, and from the drive you can work it into your current workspace. So after the copy command is executed, you should be able to see the dataset.zip file onto the left side. You can see the dataset.zip, and now you unzip this file with an unzip command, and then the dataset directory should be created on the left side. The next step is to import all the necessary libraries, and here is where we import TensorFlow, OS, this is OpenCV, NumPy, and MATLAB for plotting, and Matplotlib for plotting. Once this is executed, our next step would be to read all the images which are present, and this could be again done through a simple set of code which basically define train image and train label. So with each image, we have a label. What we have in our directory are the images of cats and dogs. So each label is either a 0 or a 1 corresponding to cat and dog. But this example is generalizable to any kind of binary classification which you may have. Once the images are loaded, the next important step we will have to do is to do the pre-processing of our data. So we can quickly, once we have loaded the images, quickly plot and see how those images actually look. And you can see if I look at my image in index 1, it's a cat image. If I look at my image at index 5001 or 5000, it's a dog image. So we have 4000 cat and 4000 dog images in this system. So the next important step of pre-processing, and here the pre-processing step basically makes sure that whatever image you have is converted into a format which can be easily accepted by the neural network. For our case, we are making all the images of square shape of 100 by 100, and we are converting them from color to grayscale, and then scaling them between 0 to 1. This is a very common practice in most computer vision algorithms. So we can jump quickly to the point here. And once we can execute this function, and then we should be able to pre-process any training or test data set as we need. So I will quickly jump towards the part where we have already pre-processed our test and train data. And then finally, we will go to define our layers of the model. And this is the key part of the neural network, which is different layers. And this is where all those key terms which we were looking at come into play. We have layers which are convolutional layers, the max pooling layers. We have the dense layers, which are fully connected layers. And together, they make a full neural network, which here you can see has five different convolutional layers and 4 different pooling layers. And I commented out one pooling layer. You can put it back in and execute and see how your code performs then. Once we are done with this, we will execute this model. And the execution of model basically involves putting in the training data as well as testing data, defining the epochs and the batch sizings which we want, and the kind of loss function optimizer we plan to use. The training is something which takes the longest time. For this data set, it took us about 30 minutes to train this model. And finally, we can see after the training is done, how our model performs in real life. And we can go online, pick a dog image, let's say, we pick one image, copy it to our workspace, and try to test its performance. So here we can see the image which we got was a dog image. And once we run through the model.predict function, which helps us tell what does the model think the image contains, we should be able to see on execution of this the probabilities of whether of dog and cat and which one is greater. So on execution of this, our model does predict correctly it is dog, and if you actually look at the numbers, it says it was 96% probability. So here's a quick example. Of course, you guys can have the notes which have all the code, and you can go back to the webinar again to closely look through it, but it just gives you a feeling of what goes in understanding deep neural networks. Okay. So we understood about how to build a convolutional neural network from scratch as well. As closing remarks, AI has ubiquitous impact and has played a major role in ophthalmology. It is very important to understand the basics as it is influencing all parts of our lives, and there is a lot of hype around it, and we want to separate the hype from reality. Important ethical and regulatory issues will come into play as these techniques become more and more popular. I strongly believe that the future is human experts and AI working together for betterment of society, solving the problems which we have with this new special tool. Thank you so much for listening. I hope it was informative to some degree. We are open for questions. Thank you.
Thank you very much, Nishant. And thank you, attendees. And attendees, if you have any questions, now is time to enter them in the question box to the right of your screen. And one attendee here has asked what is the code to enter in order to execute? This is the code that I sent to most of the list yesterday, and I put it in the chat box. I have everybody's email, and in response to your question, I will email you the code, anybody who asked me for it. So you can email the moderator if you would like a copy of the code again. Next question here, Nishant. Can you recommend some books to read on DNN?
Okay, so that's a good question. Maybe we can answer it in the email response. There are a lot of different publications. The best thing to read, I believe, is the documentation from the software platforms themselves, like TensorFlow and PyTorch, because it is such a fast evolving field. As I said, the TensorFlow 2.0 just came out on September 30th, like a week ago. So books usually fall behind. There is a famous book called Python for Machine Learning, which is very helpful to get started with machine learning projects, but the latest developments in deep neural networks are difficult to cover. I will more strongly recommend online sources versus the book here, but we can happily send out notes later as well.
Okay, thank you. Next question here. Apart from accuracy, what are other measures of the quality of the AI, apart from accuracy, what are other measures of the quality of the AI/CNN/DL algorithm that you use?
Yeah, that's a very good question. And so accuracy is obviously only one measure, and its value depends on what that accuracy is measured on. Obviously, you want to make sure your DNN or your CNN is not overfitting. So you want to be able to test it on a variety of data. You want to test how does the neural network respond to images which are slightly different from the ones which were covered in your data set. So that is a concept called generalizability of your machine learning algorithm. Of course, there are a very important parameter is speed of execution. That is, how many floating point operations does the neural network take? And another one is the memory consumption. How much memory will it take? And those become very practical even if your neural network is very strong, but if it takes too much computational power, it may not be very useful.
Okay, thank you. Is it possible for DNN to self-train?
That's so self-training is a broad question. What people call this is a self-learning concept, and there's a concept called Q-learning, where the program is given some inputs and it trains itself over time. And that's how actually the Go program trained itself to play Go. It basically took the images of the board and it plays against itself several times, trying to improve the result each time. And that was a self-learning process. And yeah, they definitely can do it. Very common in such strategy games and other things.
Okay, I'm going to take one more question here, and I will be sure, attendees, that Nishant receives all of your questions and your contact information. And for the questions about how to download the code, I will be sending those people the directions. So here's our question. Will AI be able to detect multiple diseases in scans, for example, diabetic retinopathy and glaucoma?
Yeah, there is actually already publications out there which have shown that people look at DR images and try to see if glaucoma is present. In fact, diabetes is, it does increases the chance of glaucoma based on certain studies. So from Singapore Eye Research Institute, Dr. Ting's work has tried to look at multiple diseases. One of the publications I talked about, Carmi and others, Cell 2018, also looked at multiple diseases. So yeah, AI can definitely look at multiple diseases at the same time.
Okay, and thank you very much. And you've gotten a lot of comments here on what an excellent presentation you gave, Nishant. So I want to thank you. Dr. Nishant Mahan of Wasatch Photonics, our presenters, and all of our attendees for participating today in our webinar on AI and OCT hosted by Photonics Media. Thank you.
Thank you so much, Robin.